Today, we'll be investigating inductors in DC circuits. An inductor is a passive electrical component which stores energy in the form of a magnetic field, charged up by the flow of current. Inductors typically consist of a coil of insulated wire wound around a core, and electrical diagrams are denoted by the use of either of these two symbols. In simple terms, inductors produce an electromagnetic field which opposes changes in current flowing through them. This is due to the change in current causing a change in flux, in turn resulting in an opposing EMF produced by the coil as per Lenz's law. As such, when current is increasing through the coil, also known as the charging phase, an EMF which opposes the current will be induced. This property is referred to as inductance, represented by the letter L and measured with an SI unit of henries. The greater the inductance, the more energy can be stored by the inductor. Once the circuit reaches steady state, the inductor has no effect and effectively acts as a short circuit. This can be seen in the storage and decay phase, where in the storage phase, when current is first introduced to the circuit, the EMF opposing the change in current is at its highest, as the current is increasing at the greatest rate. It is crucial to understand that the EMF is equal to the magnitude of the rate of change of the current within the circuit. This is also seen in the decay phase, where the opposing EMF is at its greatest magnitude when the current is decreasing at its greatest rate. The time taken to reach steady state, or when no further EMF will be produced, is represented by 5t, or 5 times the time constant. To calculate the time constant, we simply put the inductance of the circuit over the total resistance of the circuit, which will produce a value in seconds. To calculate the inductance of a coil, we can use this formula, and when adding inductors in series, we use this formula. Additionally, when adding multiple inductors in a circuit that are in parallel, we use this formula, where we find the reciprocal of each of the reciprocal values of the inductors on their own added together. This process is the exact same as when adding resistors in a circuit. Common applications include for sensors used in red lights, induction motors, transformers, and for small energy storage needs. In this example, we'll calculate the time constant. The inductance of the circuit is simply 100 millihenries, since there is only one inductor, and when adding all the resistors together, we get a total resistance of 1050 ohms. To calculate the time constant, we divide the inductance of the circuit over the resistance, as can be seen here, and when done, produces a value of 95.2 microseconds for the time constant to occur.